Так, все, можно начинать?
Получается, да?
Well, so sorry for the late start today. Today's topic is from isomorphism. Isomorphism. And its relationship with congruent reality. Last time I mentioned it very briefly. So, what is a general situation we are going to deal with? Assume that we have an oriented vector bundle over a smooth manifold. And all things are oriented. Manifold is oriented and the vector bundle is oriented. And actually, there are several possibilities to look informally on what is a vector bundle. But first, what is a manifold? A manifold is something which is locally modeled by charts. Well, this is a very standard definition that for each chart you have got a homeomorphism with some domain in Rm, yes, and if you have, this is completely the same way to say about charts or to say about local coordinates. If you have homeomorphism with this domain in Rm, this is exactly local coordinates in this chart. And so, on the intersection, such composite map should be a diffeomorphism. This is standard definition. Again, standard definition for vector bundle is that vector bundle is something which is locally modeled by manifold is locally modeled by domains in Rm, and vector bundle is locally modeled by domains. What is a local chart in vector bundle? A local chart in vector bundle is some domain in Rn times the fiber. So vector bundle is something which is locally modeled by such objects. And what can we say about this? So we have this. Let us distinguish between a chart and its image in Rm. So I also prefer here to have V alpha, and this one is mapped on some part of our vector bundle. And if we have another chart of such type, then as usually on the intersection we have some map. I use dashed line here since it's defined only on the intersection, directly as here. And here we could have an arbitrary diffeomorphism on this path. What can we say about vector bundles from this viewpoint? So from this viewpoint, we have some set of coordinates x here and set of coordinates y here. And in the case of an arbitrary manifold, the change of coordinates is just an arbitrary C infinity, an arbitrary diffeomorphism between a domain in Rm and another domain in Rm. What is the difference with the case of a vector bundle? In vector bundle, we naturally have coordinates in every such. We always have this splitting on coordinates on the base and coordinates on fiber. Let us denote them by different letters, so we have coordinates x1, xm on the base, and I will use x for the total set of these m coordinates. And I have linear coordinates t1, tn on fiber, and again this is t. And an important thing is that we can look on vector bundles. This is one of the possible ways to think about it. That this is a manifold, but with restricted with a restriction on possible transition functions. Here we may have arbitrary diffeomorphism, and what can we have here? If we have one set of coordinates of such type and another set of coordinates of such type, then which changes of coordinates, here are n, I'm sorry, here is dimension of fiber, which changes of coordinates are allowed? If we insist that these are not arbitrary coordinates, but these are coordinates on the base and these are linear coordinates in fibers. What is allowed? What is allowed changes of coordinates? First of all, coordinates on the base can be any expressions on coordinates on the base here, but only on the base. This y's can depend on t. So we have y equals an arbitrary c infinity functions. Here, of course, functions which have an inverse, but these are c infinity diffeomorphism. But what is for S? For S, we have an arbitrary, a linear. S coordinates must be expressed linearly from T, but the coefficient may depend smoothly on base point. So we have some matrix depending on N and T. So we can look on the vector bundle as on a manifold with such very restrictive changes of coordinates. So this is just the standard definition. This is nothing but a standard definition. Vector bundle is thing which is modeled by part of manifold times Rn, and when we glue them, then on each fiber we have a linear map. This is exactly those. And so when we consider something in Durant homology, in vector, in differential forms and so on, if we deal with arbitrary manifold, then we can do only, if we want to define something in coordinates, we can do it if it is invariant with respect to all changes of coordinates. But here we can do in coordinates everything which is invariant with respect to only such changes of coordinates. So vector bundle is manifold with additional structure. And I want to do this was a preliminary for one particular definition. A particular definition is we need a homomorphism of integration along fiber. Integration along the fiber. Assume that we have a form. Any form in coordinates can be written as not any, but basis forms. Any form can be written as linear combination. I'm interested in forms of E. E is a smooth manifold, and I can study forms on it. Any form can be written as some linear E. In local coordinates, it can be written from coordinates on the base and coordinates on the fiber. Well, what is I would like to integrate along fiber. So I would like to integrate along all variables t. So how can we do this? It is more or less natural idea that there is an important case when here we have all coordinates t. Then we can rearrange them so that we have just dt1, dt2. It is natural to integrate this in the following way. We can integrate f of x t in a usual way along Rn and multiply it by this okay. But this is a natural candidate for integration along the fiber. And it is also natural that if we have not enough coordinates to integrate, then we cannot invent anything interesting, and the only idea is that if we have here less than n coordinates of type t, and q is less than the dimension of the fiber, then we only can integrate it to 0. Claim is that this operation is well defined. Why? In this way, here it is very important that we can use only changes of coordinates of this type. This is a local operation, local in the sense that the resultant form.
We've converted some part, yes?
Yes, that's next point. Let us for a moment forget about it and just assume that all integrals exist. I will return to this question later. There are two variants here, but for a moment let us forget about the problem with non-compactness. Let us just look on why it is well defined. Well, the matter is that if we consider such change of coordinates, then look, first of all, if we have a form of the second type, that there are smaller than n number of dt, then after such a change, we again have the same property. Yes? Maybe it is more convenient actually to substitute here. It is more convenient to express vice versa. X to y and t some b of y s. Well, if we express t from s, then when we substitute here, the number of dt's can become smaller since we can differentiate by y's, but cannot become larger. So if it went to 0, then it will go to 0 in new coordinates as well. And for such forms, we in a sense have only linear change of variables. The matter is that the dependence of this by y is unimportant. Look, when you rewrite dti's through y's and s, you can differentiate along by y, by one of y's. But then you get into these types of forms. Then the numbers of differentials along fiber become smaller. So they do not contribute to the result. So what contributes to the result? Contributes the terms which contribute are those as it wasn't dependent by y. We do not need to take into account the dependence by y. We can only write dti's through dsj's. Then this is a standard linear change of coordinates, and of course the integral is the same. So it is just a standard exercise. I don't want to write it explicitly using all indices and so on, but it is a standard exercise here that this operation is well defined. Just on the level of forms. The only thing we need is that, of course, to take this integral, first we need orientation. This is, but I said that all our objects, manifold, and actually we do not need orientation of manifold here. We need only orientation of vector bundle. Actually, this is a useful remark that at this point we do not need an orientation of manifold. We need only orientation of vector bundle. Orientation of vector bundle is needed to take this integral to choose the sign, but orientation of manifold is never important here. And second is of course the question of compact support. Of course, if we have an arbitrary form which goes to infinity, then we can integrate, and it is not well defined. There are two types of situations when this is well defined. First situation is just compact support. Yes, this is denoted by if the projection is pi, then this one is denoted by pi with lower star. So we get a well-defined homomorphism from forms with compact support on E to the forms with compact support on M, but dimension, the degree of a form becomes lower, decreases by n, since we integrate n for these differentials are integrated, so we get just k formed from k plus n form. But there is also another and actually more important situation when this also works. And the situation is as follows. Actually, we would like to work with arbitrary forms. We would like to have arbitrary forms here on the right. Of course, we cannot take arbitrary forms there, since an arbitrary form we just cannot integrate it. It's no hope to integrate if it is not compactly supported. But look, here we need to have only local compact support along files. We do not need compact support in direction of the base to take such integral. So a good idea is to give a precise definition. A precise definition is as follows. This is denoted by CV of E, and it is called forms with compact vertical support. Compact vertical support. What does it mean? This means that for any point in M, if a form belongs to here, if and only if for any point in M, there exists a compact neighborhood of P. We just can think of it as a compact ball around P.
1 quantifier.
Well,
1 quantifier.
Oh, sorry for I say for any for any point there exists a V is a compact neighborhood of E. Well, with the following property that if we take pre-image of this V, pre-image of this V is a non-compact thing. If V is small enough, then we can just think of these pre-images of V times Rn. With the following property, that if we take a pre-image of V and intersect it with the support of phi, then this is compact.
So we need projected.
Yes, this is not for an arbitrary manifold. There is no such object for an arbitrary manifold. This is for vector bundles. So if E is a total space of vector bundle, then we can introduce such type of forms. So this is compact. So support of phi, this is compact. This is the definition. So this is some intermediate condition between compactly supported forms and all forms. Of course, compactly supported forms are contained in vertically compactly supported forms, and they are contained in all forms. And look, this is exactly what we need to take integrals. If we are allowed, if this is compact, then we can write down the same formula. We do not need any compact support in the direction of the base. And what we get again another type of integration of the fiber is from this compactly vertically supported forms of E to arbitrary forms on M. Because now we do not have any compact support in the direction of the base, so we can get arbitrary form. These are two variants. Look, starting from and another important fact, which is also follows immediately from the definition, that this P star commutes with the exterior differential. Again, look, if you take an exterior differential of such form, then of course
No, so
it went to zero and its differential also went to zero.
So no.
No. Actually, I'm sorry. When we take we need to be we need to take care of this case. When you have actually vice versa with this form.
Different differentials, because the forms are different.
Yeah, of course. Computes with D means that. What does it mean? Let us write down it more explicitly.
I think we have checked it in special case for Poincaré.
Yes.
It is the same.
Yes. Let us. It doesn't matter for both cases are equivalent. So of course we mean that we can integrate along fiber. Here we have differential for E, yes, which goes to, and here we have differential on M. Commutativity means exactly this. Look, for the forms of the first type, it is obvious. The matter is that when we take differential here, we can differentiate only on x's. All t's are already here. If we differentiate this by t, then we get dti and we get just 0. So only only derivatives along axis enter here, and so we get exactly, this is just exactly formula that derivative along x commutes with this integral. Nothing but this. But for the second, it is somewhat more interesting. The matter is that taking here a derivative, assume that the number of dti's here is exactly n minus 1. Then taking a derivative by 1 ti's here, you can get form of the first type here. So the question is why it still integrates to 0. Let it be an exercise. I just don't want to write it down. It's an easy exercise to check this commutativity for the type 2 form. Okay. So what does it mean? Once we have a map which commutes with differential, we immediately get an induced map in cohomology. So we get two types of maps. Look, we can use all forms to define usual theorem cohomology. We can use compactly supported forms to define cohomology with compact support, and we can use this strange type of forms to define new cohomology, cohomology with compact vertical support, and this type of cohomology, it seems to be exotic. Why do we need such exotic thing? And in fact, it is in some sense auxiliary thing. It is not interesting by itself, but it turns out to be very useful to understand. So we will see why it is useful. So we have these two induced maps. We start from compactly supported cohomology of E to compactly supported cohomology of M of dimension n of n small dimension, and we start from compact vertically supported cohomology of E to usual theorem cohomology of M, and our main theorem is that these are isomorphisms. On the level of cohomology, they are isomorphisms, not on the level of forms, of course. So these are isomorphisms. Well, before discussing this theorem, let us discuss one important formula. I will return to this theorem in a couple of minutes, but let us start with a very, very important formula, which is rather easy, but it is very useful. It is called projection formula. form on the base. And we have a form with compact vertical support on the total space. I would like to have compact vertical support to be able to take this integration on file. Then there is the following very useful formula. So we would like to multiply these two forms, but we have two possibilities to do this. They are on different spaces, so we can either raise tau to E, or vice versa, push omega to m. So let us write down these two possibilities. We can, first of them is that we take pullback of tau, we get a form on E, not necessarily with compact vertical support, but when we multiply it by omega, we get a form with compact vertical support. And now, and another way is that we just take tau, but here we integrate omega along fiber. So this is a form on the base, and this one is the form of the fiber on the total space. The claim is that if we integrate along fiber this form, then we get exactly those. This is just equality on the level of forms. It is just on the level of forms, and it is completely trivial. It obviously follows from here. The matter is that, look, tau is a form of the base, so it doesn't have these DTIs. It has only, it depends only on variables x. So this is immediate from definition of the integration of the fiber. So it is easier, but it is very useful. We will use it today several times. Okay, and what is about those theorems? Actually, this is again a theorem of Mayer-Vidor's type. So it can be proved via induction by covering. Again, the situation is as follows: that the theorem is true for an arbitrary manifold and an arbitrary. Yes, the only thing which we need is that bundle is oriented. I stress once more that we do not need that a manifold is oriented. M can be oriented or not.
To integrate.
Yes, to integrate means that bundle is that fibers have prescribed orientation. But we do not need anything about the orientation of the manifold itself. And actually, it is true for an arbitrary manifold M, but I will prove it only for manifold of finite type. If it is not of finite type, then we need to go to take limits, and I don't want to speak about it. And actually, it is not completely true that I will prove it, because it is again the same, completely the same argument that we discussed several times. So I just say some words about how to prove it. I don't want to repeat the same five lemma once again. First of all, of course, both these things are true when the bundle is trivial and the manifold is Rn. It is just the trivial check. That if this is based on induction. So first, base of induction is that suppose that, in fact, all bundles over Rn are trivial, so we do not need to require this, but actually that M is Rm and E is Rm times Rn. Yes, this is base. When we have this situation, then of course, look, the only dimension where this homology is non-zero. So let us start with compactly supported case. For compactly supported cohomology, we have here the only possible when it is non-zero, only when this is 8%. We have discussed it, the compactly supported cohomology of Rk exists only in dimension k, and this is R, and so sorry, that's for yes, that's for this. And of course, when we take differential, what does it mean that how the isomorphism with R looks like? It is just the integration over the whole manifold. Well, but we can integrate first by coordinates from here and then by coordinates from there. Of course, we get the same.
No, it is Poincaré.
Yes. That's the Poincaré lemma. Except we have nothing here. Nothing more here. Okay. So this is completely trivial, but this is an isomorphism. Well, for the second situation, it is somewhat less trivial. Look, here we need to have compact vertical supported cohomology of Rm times Rn. What does it mean? This means that we allow arbitrary supports along this Rm, but compact support. So this is the fiber. In this case, we need to specify it with the fiber. Good exercise that this is. We do not. This object. This is again a type of Poincaré lemma. This object doesn't feel this M. These directions which are not compactly supported, we do not feel it, and we have here an isomorphism with just compact supported homology of Rn, so of dimension, the same dimension G, and so this is R when we have when this is n and this is 0 otherwise. And again, integration along fiber gives an isomorphism with G minus n of Rn. Again, this is when this is 0, then we get R and 0 otherwise. So base of induction is easy, we just check it. And then we again would like to come from, so what do we need to prove this theorem? We need to use Meyer-Victoria sequences. Which Meyer-Victoria sequences? First, for compactly supported case, we have compactly supported variant of Meyer-Victoria sequence. So if our manifold is the union of U and V, and we already know the assertion of the theorem for U, for V, and for the intersection, and we would like to prove for M. Yes? Then we would like to write down the compactly supported version of migratory sequence. I recall that the compactly supported is in the following direction, that we maps are induced by inclusions. So we start with u time v, yes, and we have this. We go to u and to v extended by 0, then you go to u cap v, and so on, migratories. And we can do the same. We should write two migratory sequences, one for u, v, and m, and another, we obviously have that E is the union of preimages of u and of v. And so we write down one migratory sequence, this one. We write down the second for E. Integration along fibers gives a map from this migratory sequence to that. And then we just use find them. I don't want to write in all details. This is for the first case. For the second case, the situation is somewhat more difficult. The matter is that, of course, for M, we also have. Oh, I'm sorry. Here it was compactly supported. Yes. If it is not compactly supported, if we come to the second case, well, if we come to the second case, then we need to delete C here, and we need to reverse all arrows. In non-compactly supported case, arrows are in the opposite direction, and we have migratory sequence in another direction. The question is, what do we have here? For M, it is easy still, but for E, we need to take care. The matter is that for compactly supported cohomology, the migratory sequence is in one direction, in arbitrary in another direction. What is in this compactly vertically supported? The correct answer is as follows. First of all, if we consider just arbitrary decomposition of E into two sets, there are no good migratory sequences at all for compactly. But here we do not have an arbitrary. We have very special decomposition. We require that both parts are preimages of some subsets of the base. And this is very special. In this special case, we have migratory sequence with the same standard direction of homomorphisms. Why do we have this? This is sorry. Let us write it down. If we take compactly vertically supported homology of preimage of intersection, it doesn't matter. Preimage of intersection is the same as the intersection of preimages. Then we get here compactly vertically supported homology of preimage of U and on preimage of V. And here we have compactly vertically supports of the whole E. Why this is?
We more or less take that sequence for the normal homologies of E, and then restrict to.
Yes, and the only thing we need to check that when we take that the maps are well defined. If we take what was the problem? The problem with compactly supported cohomology was that if we take a form, look, you have a manifold M, and you have a form which has compact support. Well, for instance, its support is such disk. Well, then we restrict it to a neighborhood. Let's just take a small disk, but the support of restriction is not compact. It's just U itself. Well, this was the problem with pullbacks of, we have no good pullbacks for compactly supported forms. But here we have not arbitrary manifold, but we have our, not arbitrary map. Our map is the inclusion, say, of these two E. And if our form has compact support in vertical direction, then of course its pullback also has compact support in vertical direction. No problems with this.
It's perfect on the other set of coordinates, on the original ones, because it is an inclusion test.
Yes. So this is just very easy fact, and in this situation we have my sequence, so we can proceed by induction again instantly. So this is not a hard theorem. Well, but what is nice here, up to now it is more or less not so interesting, but what is nice here that we can study the reverse isomorphism, and it turns out that it has a very nice form, and it is called Tom isomorphism, and it is very useful.
Sorry, maybe there's a typo that in the special case that you want every cohomology class to be the vertical one. I mean the last one for E should be also C.
Yeah, I'm sorry. This is just a misprint. Yes, of course. Thank you very much. Okay, so now let us. Most of things I would say work in this situation as well. Not exactly. Sorry. At this point, let us concentrate on the second one. Why second one is more important? The matter is that what is a very nice property of usual Durand homology, which is absent in compactly supported case. In usual Durand homology, we always have one. This is actually any kind of this homology is a ring. We can multiply forms, but this is a ring with unity. We always have one. We can take zero form, which is identically one, and this is, of course, so this is a ring with identity. So let us concentrate on this type of homology. And this is actually why this one is more important, because we have identity, this homology. And, well, once we have an isomorphism, and we have some important element here, it is natural to consider the corresponding element here. So, in particular, we have integration along fiber yields us the following, that nth compactly vertically supported homology of E, if we integrate along fiber, then this is an isomorphism with zeroth homology of M, and let us, we can assume that M is connected, then this is just R. But in any case, it has one here. And we can consider its preimage. Its preimage is usually denoted by phi, capital, and it is called Tom class. This name after an atom. First of all, well, what are important properties of this class? An important property is the following. A nice property is that we can write down, we can consider inverse isomorphism. It is called Thom isomorphism. So this is just, by definition, this is P star inverse in cohomology. And a nice situation is that we can write down it explicitly. If we have a class here, which is, well, I would like to write down a not very good formula, but I would like to write down it like this. But, well, I don't know, this is very bad, but I would like to write down like that. But this is still not very good, since these are homology classes, not forms. But the formula is on the level of forms. Oh, sorry, this is not, this is fine. I claim that the reverse homomorphism from the homology of M, not only from the first homology, but for an arbitrary homology. We can take arbitrary homology here and arbitrary homology there. The reverse homomorphism is nothing but multiplication by this Thom class. But to be precise, we need to take a form here. We need to raise it to E, to take the pullback to E, and then multiply by phi. Look,
Well, by a representative.
by a representative of phi. So to be precise, if we need to take here a homology class, yes. We need to take here a homology class. No. And we need to take here a form which represents Thom class. But actually, it is very not so pleasant to write down these brackets always. So I will prefer to usually to denote the Thom class and Thom forms by the same letter, though it is not completely. Why this is true? So, first of all, this is a well-defined map. Well,
no, we can check by projection.
yes. This immediately. First, let us look. This one is an arbitrary form. Well, but on E. But when we multiply by a representative of Thom class or by Thom's form, then we get compact version of support. That's okay. So we actually get into there. But why it is a reverse isomorphism? Because if we use a projection form, I'm sorry, it is really convenient to denote Thom's formula by theoretical. I prefer not use the same letter form of class. And then, let us be. Then we get what we get by projection formula. We get here omega times this type phi. Well, but this is one just on the level of forms. Why?
No, by definition.
By definition, the matter is that by definition we know that P star phi is a zero form that represents cohomology class 1. Yes, but closed zero form is constant function, so it is one just on the level of forms. Not on the level of. So this is just one unit. So we return exactly to the same.
Does projection formula says exactly that P star
Yes,
is
because P over star is an isomorphism, so it has the inverse.
okay. Does projection formula say that P star is homomorphism of models for ring?
Yes, yes, of course. Yes, yes. So P star is actually a homomorphism of what? Yes, thank you very much. I forget to say about it. This is a very important point of view that this is actually says that P star is homomorphism. We have H star of M module structure here, and it is given by this formula. We can multiply by forms of the base by pushing it back, pulling them back to E and then multiply. And projection formula just says that this P star is homomorphism of modules, and hence vice versa, it is always also a homomorphism of modules. Well, so we have this property, we have proved this, and what is important here? First of all, this construction allows us to obtain a first characteristic class. What is a characteristic class? Characteristic class is a possibility to produce in a natural way homology classes of the base from a bundle. We have a bundle and we would like to produce homology classes of the base so that it is factorial with respect to maps. Well, and how to do this? Well, we have one homology class which is of course factorial. We just can take one. It is not interesting. It is trivial. But if we look on this one, then it is obtained from some class by integrating it along fiber. So we have this possibility to integrate classes along fiber. Some class is something which is defined canonically, not form but class. But what can we do? We can take the square of it and then integrate along fiber. Then we get something non-trivial. We can get something non-trivial. So we get something. The square just in cohomology, so the square on the level of forms, this is the square of phi times phi. Yes?
Isn't it 0?
No. Well, that's a good question and a good answer. Of course, it is 0 if the degree of phi is odd. If the degree of phi is odd, then this is skew-symmetric and so this is trivial. So, if the dimension n of the fiber is odd, then this construction is not interesting. But assume that n is even. Then this is commutative. So there is no reason why it's 0. Of course it's 0 if phi is monomial, but phi can be a sum of several monomials. So what is this? This is an element of nth cohomology of M, nth general cohomology of M. And this is denoted by E of our manifold by definition and called the Euler class of the bundle.
So I don't get it how that after pi over star it locates in degree n cohomology.
the matter is phi locates in degree n. Phi itself
Ah.
has degree n.
Mhm.
I'm sorry, here it was n. Yes?
Mhm. Right.
Phi itself locates in degree n. When we take square, it is in degree 2n. Then we integrate along fiber and get into dimension n. What are the properties of this Euler class? Look, actually, let us start with understanding an easy thing. How, well, we have defined Tom class, but of course, to work with it, we are interested in Tom forms. So Tom form is just a representative of a class. Well, and assume that we have a form in compactly vertically supported forms on E. How to understand whether it is a Tom form or not? We just need to check whether it integrates to 1 or not. Yes? I claim that this phi is a Tom form. So Tom form means that it represents the Tom class. If and only if, this is what we have discussed just now. It should be 1 just on the level of forms. Integral, the matter that P star of phi first. Yes, and sorry, I forget one important thing. This phi, and of course we would like to consider only closed forms. Yes, so we need to add this condition, and yes, and that's enough. If we have a closed form which represents Tom class, then it necessarily has this. Yes, and vice versa. If we have any form with this property, then of course it represents Tom class. So it is just some condition how to check whether this is a Tom form or not. And this condition immediately implies the following. Suppose that we have an important thing is pullbacks of vector bundles. Assume that we have a vector bundle over M, and we have some map from some another manifold N to M. We can all maps are C infinity in our considerations. Then we have this pullback, and of course we have pullback from compactly vertically supported forms here to compact vertically supported forms here. If the form had compact vertical support, then it's pullback again. Yes, compact vertical support. And I would like to say that of course under this pullback map, both conditions preserved. If we had a form which is closed and which integrates to 1 in any fiber, then the same is for pullback, of course. That immediately implies that Thom class, on the level of classes, Thom class lives here, yes, and Thom class for F star of E lives here, and on the level of the homology, just we have this map, and Thom class here goes to Thom class there. So we just have that. This is F star. So F star of Thom class for E equals Thom class for F star of E. But then the same is true for the square of Tom class. And integrated on fiber also is preserved by this pullback. So this immediately implies that this pullback of the Euler class is exactly the Euler class of the pullback. And actually, this general, this is exactly a functoriality which is in the definition of characteristic class. A characteristic class is by definition the situation when we assign with each assign to each vector bundle some cohomology class in such functorial way. If we manage to do this, then we get a characteristic class. So this Euler class is the first example of such characteristic class. Well, that's the first profit from Tom. Oh, sorry. I again forget about time.
And it's not streaming. Actually, it's not streaming.
Sorry?
It's not streaming. It's not working.
It's not working.
But I have your voice record.
Well, but anyway, we have only 3 minutes, yes? Well, I'm sorry, I didn't forget. I thought I need to finish in 20 minutes. Yes. So we have no time to discuss the relationship with planetary duality now. I'm sorry. Yes, then the only thing which I want to say now is that the first, when we look on all this stuff, the first idea is that, well, assume that we have some particular vector bundle and we would like to construct its Tom form. The first idea is that it should be easy. Well, we have it locally, of course. Locally, it is not hard to construct using some function like that. It is not hard to construct some form on fiber which integrates to one. It's more or less trivial. Then we can try to take partition of unity and okay. So in coordinates we locally write it down. Then we need to take partition of unity and take something like that. That doesn't work. Why? And it's important to understand that doesn't work. In general, at least it works very, very non-trivially. The matter is that it is rather easier to guarantee this condition, but it is difficult to guarantee that at the same time. If you try to do something with partition of unity, then you will lose closedness. Locally, you define closed forms, you try to average them using partition of unity to take some linear combination. But you lose this one. And that's not so easy to construct Tom form explicitly in examples. Actually, there is one situation when it is not so hard. It is the situation of two-dimensional bundle. One-dimensional bundle is not interesting when it is oriented, then it is trivial, so it is not interesting situation. But two-dimensional situation is maybe the only situation when it can be done by hands in a rather good way. And I think we will discuss this during today's seminar meeting. But now let's finish the lecture. Thank you. Так, чего, ничего не писал, да?
Там проблема такая. В общем,
Yes, okay, I see this means
it's okay, it's recording on the notebook.
А,
oh,
может тогда...
Мы потом выложим просто.
Окей, тогда не страшно. Так, well, when we have a break, I have one technical
It's downloaded.
question.
I don't know.
I don't know, maybe
Look,
Yeah, it's
for
okay,
the
it's
next
okay.
2 weeks,
It's recording here.
I will not be in Moscow. I'm going for a conference. So, of course, there will be no lectures in this room, but there is a possibility to give these lectures online. But first of all, concerning seminars, I certainly the seminar online is somewhat nasty thing. I don't want to do it, so just cancel that for good. But concerning lectures, the question is about time. As far as I understand, it is most probably not so convenient to you to have online lectures in the middle of the day. And for me also on the conference. So is it possible to find some convenient time, say in the evening or something like that? Or it is not so easy to find time?
No, I think we can decide in the chat.
how you have.
You have got some chapters.
We can
So maybe the second problem is that on the conference where I go, still there is no schedule, so I don't know my schedule for the next week. I was completely sure that I look on it and we decide, but there is no schedule by now. So maybe we do it by email. I just chat на Telegram.
А может вас тут добавить в аудиторию?
Мне Telegram нет, и очень не хочу оставить. Так что... Давайте, я напишу в этот самый по имейлу, а вы можете между собой, если обсудите.
Ну, это четверг положительно.
Ну, предположительно, да. Вот. Если в другими теми сложнее. Да, если вдруг окажется, что нам всем четверг неудобно, ну, в общем, посмотрим, попробуем организовать что-то. Но в любом случае, здесь вот 2 недели не будет. Следующий нет, просто чтобы они приходили, что чуть-чуть. Ладно, надо сейчас перерыв. In 3 minutes.
No, it's recorded on the notebook and we will publish it on the YouTube channel later.
Oh, yes, yes. Do you know this? Do you know this graph? I thought you have this talk about the genus of embedded
Yes.
graph.
Yes.
Yes, I'm recently reading this.
Yeah. I met this graph of course. Yes. Yes.
So do you know how to prove it?
Oh.
You can see it.
Oh. Well, how to compute this equation? It's just number of vertices, which is, well, you know, yes.
What's for? Oh,
For this polygraph,
yeah.
you know, number of vertices, number of
Oh no, it's
number of edges and number of triangles is related
yes,
to, and just compute this.
no, it's not the asking this. I forgot my. Anyway, just read it. Please read this paragraph.
Yeah, the matter is that we don't know whether it can be embedded, and so the top faces are triangles. So yeah, I understand this problem. So if it is embedded in this way, then of course its characteristic is exactly those now, but. There's no reason why there is such an embedded. And so the minimal genus can be actually.
Don't you think if I point at this, it should be the reason they make this conjecture?
Yeah.
Did you read this?
No, I didn't read this one, but I heard about this Mohart conjecture.
Oh.
No, I never read this article.
Сейчас?
Oh.
Yeah.
Yeah, by the way, I'm now trying to learn what you lecturing last year.
Yeah. Yeah,
But
that's
maybe
that's
next
that's
time,
that's
I want to
yeah.
have credit for this course. Can you add me to your mail list?
Can you just write me
I write
on
to you
email?
many times.
Yeah, can you write once more concerning this precise course?
Yes, I write.
No, the matter is that till now I send nothing to this list. So you are in the list, but I just haven't. I will write concerning the lecture time for the next lecture, and of course you are on the list if you're. Well, let's start. Let's continue. Let us for today have rest from CPM. but maybe we will return to it in the end, because when we consider well, why we will return to CPM, because now I would like to discuss the case of two-dimensional vector bundle and to obtain explicit expressions for top class and project class in this situation. But of course, the main example when we do this, the main example is CPM, because over CPM we have one-dimensional tautological complex vector bundle, but one-dimensional complex vector bundle is two-dimensional real vector bundle. So we will apply this for CPM, but this will be later. At the moment, let us start with the following situation. So we have a manifold, and we have two-dimensional oriented vector bundle over it. And what we want? We would like to write down the Tom class explicitly on the level of using some, say we have here a good cover. And so we may introduce whatever we want. We would like to, we would like to consider good cover. We have here partition of unity and so on. But our goal is to try to write down the Tom class from all this information. So the matter is that in a real example, say we take CPM, and it is not so hard to write down a particular partition of unity, a particular charts, and so on. So we want to be able to write down Tom class, and then the Euler class, of course. When we have Tom class, we more or less automatically have the Euler class. Let us start. I suggest first step, and then I hope that you will try to do the next steps. The first step is that, okay, 2 is too much. It is not that easy to work with two-dimensional things. It is easy to work with one-dimensional things. How to reduce the dimension? To reduce the dimension, first of all, we always can assume that we have a scalar product in this. We can introduce scalar product in this vector bundle. If we want to do it explicitly, then we again can do it via partition of unity. In this situation, there is no problem. We just in local chart, we just take standard scalar product, and then we just take the combination of scalar product corresponding to chart alpha with coefficients rho alpha. This is a well-defined scalar product. No problems. The only problem with Tom class is that we need to consider this condition and indicate better. But for scalar product, no problem. So we may assume that we have a scalar product on our vector bundle, and if we have got a scalar product, then well, look how to choose form which integrates to 0. Form which integrates to 0. Form which integrates to 0 behaves on this. Well, let us consider what I want. I would like to consider polar coordinates in this R2. So we have just pole. In R2, we have polar coordinates r and phi. Yes. And the main idea is to try to how to forget for a moment about this stuff. How to write down a form which integrates to one. Yeah, I would like to write down two form which integrates to one on such R2. Okay, just trivial question. How to write down form on R2 which integrates to 1. This is just some function like that times dr dx dy. Yes? Some cap. Some function f h of x y dx dy. And the first step, how to reduce the dimension. I would like to say that we can take this function to be it is called radially symmetric. It is symmetric with respect to all directions. We may take so that this one
No, but it
depends
doesn't depend on
only on r.
No, we
Doesn't
can-
depend on phi. We can choose this.
We can choose like one no
We can choose this explicitly. I prefer not the standard. Standard one is something like e2 squared. This is bad since I want to have complete support. But well, it is rather easy to write down explicitly by just using some function h, some particular function h. And this is the same as actually I can rewrite it with another function h. I can rewrite it by okay. I can write form in this way. Yes. This is not the same h. This is the previous h multiplied by r. So for this h, it is we would like to have h of 0 is 0. Yes. And also some easy property of h. Well, but the first idea is that okay, once we have introduced scalar product. Look, of course, r and phi. Now let us return to bundle. Of course, r and phi are not uniquely determined. If we have global coordinates r and phi, then our bundle is trivial, and it is not interesting to write down the Tom class or your Euler class. It's not interesting for trivial. Of course, we do not have global coordinates r and phi, but in fact, we have a global coordinate r. Once we have introduced our scalar product, r is a global coordinate. Phi is not. Phi is in each fiber. Phi is determined up to additional some cost. But r is completely global coordinate. It's just the distance to the zero section. The scalar, the length of the vector. So we can try to find our form for phi so that its restriction to any fiber is like that with some fixed h. Let us fix once forever h. Such that, okay, what should we have? We should have that h of 0 is 0, so that h of r, this is condition. This is exactly the integral of this form. We would like it to be 1, and then this must
integrate to 1/2y. So we can impose this restriction and try to find phi in this particular form. This is not the whole, this is only a restriction on phi. But let us fix one parameter, this h. It is not important which of them, just choose one. And then always consider, look, phi is not well defined by d phi, is well defined with fiber, on fiber, not on the whole. Well, so this is the first step, that we can reduce our problem more or less to we can get rid of coordinate r. Further, we in a sense this is that we from R2 bundle we can count to S1 bundle. We can think only on one coordinate, and we would like to work in terms of this S1 bundle. So this is the first idea. But then it is natural. Well, we can consider partition of unity and try to invent how to write down our formula. How to glue together the different charts. Well. I suggest you try to think about it during some time, and if there are some ideas that to discuss. If not, then I try to say something else.
Why do you start with two-dimensional bundles, but not one-dimensional?
Because one-dimensional bundle is trivial whenever oriented. We would like to consider only oriented bundles. So one-dimensional bundle is always trivial. It is not interesting. Probably no interesting example. And two-dimensional is the first situation when we have non-trivial oriented bundles.
Sorry, why we add R? Почему мы на R такие?
Because d5 is equal to
Yeah.
So when we try to integrate, we'll get like that. Oh, sorry. Sorry. I'm
Мы и так условно подразумевали, что R там включается.
So sorry. Of course, the integral is like that.
Here,
Sorry. No, when we write it down like that, and then just this one. Yes. I'm sorry.
so what freedom do we have? We can change phi over.
What freedom? Look, when we restrict form, there are two things what we do. First of all, we restrict form to the point. So we consider, we have form E, yes? We can consider it in one particular point of E. But then we can restrict to well, look. Let us consider this E. This is E, and this is zero section, which we can identify with M. Yes? If I take a point here, then the tangent space to E in this point is the vertical space plus horizontal space. And this restriction says us only what is the restriction of our form on this vertical space. But we also have its restriction to horizontals. And there are mixed terms. This is two forms, so one vector for vertical and one for horizontal. And we have freedom in choosing them. And the matter is that in this picture, red is well defined. It is the kernel of projection. It is canonically defined. But this green space is not well defined. It is any complement space. So in different changes of local trivialization of local coordinates, we can have for this green space, it can be arbitrary space complement to the red one.
Sorry, in this expression, I understand we always will have that square of tone class would be 0. Or
No,
not?
again, because of that, we necessarily have this other terms. This bar means that we forget about all terms except for vertical ones. But we necessarily have them.
So we will have some terms just in coordinate.
Yeah. The correct situation, yes, the correct situation is as follows. The correct, how to say, correct claim is that we can find our form phi in the following form. At every point, we would like to have that it is h of r dr d phi plus we can have mixed terms. We have some coordinates x's plus some. Okay, I write down something nasty. Some coordinates ai by dx ai dxi dr, where xi are coordinates on the base.
And in similar way when we replace by
Plus like that. Well, actually, one important idea is that we can have radial symmetry everywhere.
so we ignore form with
So we
dr
ignore
and
forms
something
with
from-
dr and something, and we also can try to look here that it depends on r and x, but not on phi. So we would like to have such cap. So we would like that these coefficients are independent on phi.
Почему можно выкинуть там ДДР есть?
More or less, because if we have, the idea is that why we can
Well, we can try to search for something like that and this.
why we can no at the moment let us for the first time let us preserve them, yes, for a moment. What I say that we can assume that these terms are independent on phi. And this is just by, if we have, again the same idea as we used last, the previous weeks. If we have a tone form, assume that for a
we
moment,
can choose it.
then we can, we have an action of S1 here. We have S1 which rotates this E. And if we have any tone form, then we can take an average with respect to this action of S1. And then we get to that these coefficients are independent on phi. Well, the next question is why the next hint is just try to write down what is what is the differential of this form. What can we extract from? We would like this form to be closed.
No, first goes to 0.
So sorry.
But
Yeah.
only because differentiating dr.
I feel that it seems to me that the degree for the first term dr which d5 is not equal to the rest. This has degree 2 is 2 form, right?
Yes, it's the form. But we would like to define is equal.
Странно, круто.
Можно посчитать, посмотреть, что 0 должно быть.
You would like to ask why the first ingredient is not enough, yes? Because phi is not well defined. Locally, we can consider only such function. But if we phi is not,
But the form is well defined.
no. Look, the form is well defined on each fiber, but not on the whole.
Why?
Look, suppose you have a local function phi, yes? And I get another local function which can also serve as phi. Where x1 is the coordinates on the base. It is still a good angular coordinate. Why not? In each fiber, x1 is constant, so this is a nice angular coordinate. But when you take d5, you get here the plus some form on the base. So if you just take, you can take angular coordinate locally, but we cannot take them so that they agree, their differentials agree. Of course, they agree restricted to the fiber. When you restrict to the fiber, dx goes to 0, and that's nice. But
The problem is the form dr is not closed by itself, isn't it?
the problem dr is nice for it's closed. R is a globally defined function. But this defy is not a globally defined function. Still defy is a closed form, but it is not a well-defined form. So we cannot write it on the whole manifold. We can just write this locally using near endpoint.
Там вроде получается условие, что аид не должна зависеть от r.
Аид не должна зависеть от r.
Иначе у нас там вылезает член, который ни с кем не сможет зануляться.
Да, очень похоже. Ну вот надо написать полностью.
Ну вот там.
Только это условие.
Ну еще.
То есть, да, если его написать, то можно понять, что собственно, должно выполняться.
Ну и как будто бы и жид тоже.
So if condition d5 is equal to 0, we get ai after all plus 0.
What?
We get all the ai's. That's the coefficient for the xi where d5 should be 0 because we want to exclude all the bad local coordinates.
First of all, well, when we take differential, yes, we do not get this a, you get just some derivatives of that.
Derivatives, okay.
So maybe some derivatives are 0, but I don't think like.
It shouldn't depend on both curve and x.
Yes, look, A indeed is independent on x. The matter is that the expression dxi, dx, j, d phi, well, can come only from here. We cannot get it from here because here it doesn't depend on phi. Yes.
Yes.
So it comes only from here. So what does it mean?
Но это не значит, что, ну там скорее,
It
что
means
это
dai by
скрытые должна быть четко.
j equals what? To minus, yes, dij.
Ну, we need that if we
Something like
ignore
that.
the phi, i x dxi must be close to.
Yes.
No, as from coming from.
Yeah. But look, actually, we our goal is not to understand all top forms. Our goal is to construct a top form.
So we can choose.
We can try to to search for it in some special form. No, but not in if we restrict ourselves too much, possibly there are no forms of this type. But we can try to do more than just.
So we can replace closed by exact, yeah? Something like this.
Так нам же нужно будет
Ну, то есть мы сейчас пытаемся ограничение определить.
Ну, например, да. А другой путь, another way is that, okay, look, we can consider like that we have we have some good cover, and this cover is fine enough so that over each u alpha our bundle is trivial. So over each u alpha we choose its own angular coordinate phi alpha. It is not globally defined, it is defined only on the preimage of u alpha. Then what we get? Then of course, our main idea is that we can try to start with just with the form h of r, dr, d phi alpha. This is a nice form on the over q alpha. Yes?
Yes.
So this is a form on the image of u alpha. And we can take such, say, two of such forms and try to, or three of them, and try to, to get them together using some, and also we have here some partitional unity. So we may, what is the first idea? The first idea, let us try to do it in a naive way. Naive way is like that. Yes?
Yeah.
This is nice form. It integrates to one on each fiber, but it is not closed. But let us look why it is not closed, and maybe we can correct so that it became closed. So it is reasonable to take this for initial attempt, and then understand how to change this form. So this.
So, how understand, in this case we need to look at the derivatives of partition functions.
Yes, yes.
Says how?
They of course, depend, they depend only on x, only on coordinates on the base. Yes, and of course, it is impossible to guarantee that the derivatives are zero. They are non-constant functions. And so we can start with this form and try to consider its differential. And then to try to add some terms. Well, a good question is how phi alpha and phi beta are related. If we go to some intersection, yes? Then we have, here we have some, we have different forms here. The phi alpha. So what is the relationship between phi alpha and phi beta? Yes. So it's linear. So what does it mean? Acceleration on the language of this.
No, it is that looks like we add some angle.
Phi alpha equals phi beta plus some function of
Yeah.
coordinates.
Phi alpha equals beta plus some function only of coordinates. Yes? That should help us. So we have partition of unity and you have these functions. And now once you see some function h alpha beta, what is the first natural question? Must be.
How it is related to partitions.
The first question is whether it is a cocycle, whether it is true. Of course, this is true. And the first important question is whether it is true that there is something zero.
Of course.
It is not trivial question.
No, only up to a multiplier of 2 pi.
Yes, it is not true. It is true only up to multiplier. The matter is that phi alpha are not coordinates at all. Not real valued functions. They are functions defined only after 2 pi z. So if you would like to have h alpha beta real valued function, that you do not have cosine condition in full generality. You have a very special form of it. Not precisely. This is important. In fact, if you always have this equals to 0, then the Euler class will be trivial. So this is exactly on which the non-triviality sits. Exactly on this point, the non-triviality sits.
But for d of h alpha
Yeah.
beta, it will be
Yes, yes. This is also important observation that if we look for d of h alpha, then this is a cosine. We get 0, this is true 0. Yes, you can use that. This is a good cover, so all intersections are contractible over intersections. The bundle is trivial, so on.
We can take care of only one this. Когда у нас фи преобразовывается, когда это будет сильный цикл, и поэтому у нас исчезновение будет дикс скидывает фи, для этого очень нехорошо.
Ну да, и профессионально. Да.
То есть, как я помню, надо что-то подогнать, чтобы вот эту часть вычленить. Это вот кусок. А вроде бы вот такие штуки будут выделять только как будто при больше. То есть, по сути, можно добавить часть. Ну, получается, вот эти можно забыть.
Потому что что придумать, это не будет посылка. Это было расстояние из посылки. Он живет на базе, только кусок можно завести. Он что-то такое надо учесть. Что живет на базе, совершенно верно. Yes, I would like, this is an important observation that for differentials we have honest cycle condition. And look, this is one quality repeated on the intersection. Now we need to use that this is a good couple. That this intersection is contracted.
This means that there's almost
Is constant on the intersection.
Yeah, the sum is constant of the intersection. This is the cycle and one for contractible sets. The cycle is a cabal.
But it is the compounder of the formula.
Yes.
But
I mean in another sense it's
But
cabal.
is the 2pz term is with a fixed.
It is another situation. I mean it's cabal in another way. Look, this is function of we have a triangle alpha beta gamma. Just imagine this is some function on edges of this triangle, on oriented edges for each x. This is I would like to consider dependence on alpha beta gamma, not on x. Then this is function of one h over another h and on the third h. And we know that this function is a cycle in the sense of simplicial topology. Its sum of these three oriented edges is 0. What does it mean? This means that there are some one forms. There exist one forms. Let them be xi in vertices, xi alpha, xi beta, xi gamma, such that if the sum is 0, then we can write it. Something like that. But this is an idea, it's better to do it more precisely. That's really true that we always
What
have.
you need to know for the.
Well,
What you'd use the know for the cover.
yeah, in sense, yes. So we always can write it down in such a way. Yes. Or not.
These forms live on the wall, no, on each cover.
Yeah.
part.
Non-trivial non-trivial thing that we would like C alpha be the same for all pairs alpha beta. And the question is, actually this is not so trivial. This existence is not so trivial, but it is true.
Can we choose C alpha arbitrary and then all other will be uniquely constructed?
You can choose C I. The matter is that to be honest here, what is written here? We would like C alpha to be defined on chart U alpha, C beta to be defined on chart U beta, and we would like their this equation to be true on the intersection. Intersection is so we cannot restore C beta from C alpha. But the claim is true, but we need to prove it. So there exists such one forms.
functions will differentiate them.
Yes, it will construct them by means of partition. Yes. Well, look, I don't. This is a question how to construct that function. But what is nice when we suppose we have constructed them. So first, we once more we started from angular coordinate in each chart. We take the difference between them. This is a function of coordinate x. And actually, the reason why we can choose this as function, not as is that the intersection between alpha and beta, u alpha and beta, is constructible, so we can choose it as a good function. Then we have this, and then we have this, and then this is a non-trivial part, slightly non-trivial. We have 1/4 c alpha on each chart, such that on the intersections they satisfy this. And what is a good profit from that? The matter is that if it is true, then we can differentiate it once more. We get big C alpha equals big C beta. Well, on each intersection. What does it mean? This means that the forms Dixie alpha all together constitute a closed form. It is not necessarily an exact form. The matter that C alphas are not well defined over the whole, but Dixie alphas are well defined, yes? And we get a well-defined global two-form Dixie alpha together constitute a global two-form on our manifold, on the base. And actually this is almost the Euler class. This is the Euler class up to some multiple like 2π. And if we go through all this stuff, we understand this multiple also. So we started from tone form.
So in our form of tone form, we needed this part and plus some function depending on R and this global two form.
Something like that. It is not. Yes. The idea is that. So at least now we have an explicit formulation of what we want to prove. That is an explicit formulation is as follows. That first we would like to prove that starting from this, and we arrive to this. This is already understand. We understand. Then first part we need to prove this existence of one forms of this one forms here. Yes. Second, once we understand their existence, we have that this will define the form. So claim is that up to some multiple to pi, claim that up to, well, let's form theta. Well, this equals to form. No. Theta is already, well, psi, yes? Up to multiple, psi represents the Euler class of our bundle. And actually we would like to prove this claim and understand the multiple. And to prove the claim, we need to construct from all this stuff, from C alpha, from rho alpha, we would like to write down the partition of, to write down the Thom class. Thom class is not interesting in itself. A more interesting thing is Euler class.
Yeah.
But to understand that this is indeed an Euler class, we would like to write down Thom class and then check that we did get this Euler class.
Это же вот утверждение, то, что существуют единформы такие, это утверждение, что первые гомологии пучка единформ нулевые.
Да. Да, там есть.
Гомологии пучков формы не связаны как-то с обычными, ну,
Ну, конечно, связано, потому что у нас все время есть куча точных последовательностей, у нас просто это постоянно пучок. Но всегда можно про это так думать. Вот, то есть, и у нас возникает куча как сказать, точных последовательностей, когда у нас стоят два непостоянных пучка, а фактор постоянно. Ну, сплошь и рядом. Не знаю, целоморфной функции. Мы берем экспоненту голоморфной функции. Это просто пример голоморфной функции, не обращающейся в ноль. Да?
И ядро постоянно.
А если вы возьмете фактор по образу, то вы получите... Сейчас меня заклинило. Секундочку.
Если мы про голоморфную, то вроде слева z должен быть. Ну, z в голоморфной целая звездочка, и это точно тройка.
Да. У нас точно тройка, правда. Это вот они вот здесь вот гомологии пучков. Гомологии стреляют пучков. Ну, там, понятно, на 2 пи умножать. Вот такого как бы сплошь и рядом полно. То есть, нет, поэтому здесь все, конечно, завязано, сильно как гомологии пучков обсуждать не будем, но некоторые базовые базовые вещи здесь возникают, но это несложно и как бы из общей науки понять в данном случае. But this Xi indeed can be written from partitional unity. It is not a problem to write them down. Actually, a real goal is to write down Euler class in terms of partitional unity, in a sense. In terms of partitional unity and also this this H alphabet, they have information from the bundle. Partitional unity doesn't have any information from the bundle. Together, this H alphabet and partitional unity give us all the information.
We should add to... Мы должны там добавить как раз класс Эйлера, потому что фи квадрат должен приходить в класс Эйлера.
Да.
А там интегрируется в единицу как раз.
Да. Совершенно верно.
То есть, по сути, нам надо объяснить, что если мы возьмем D вот от той формы, мы получим что-то с точностью до вот класса. Ой, не класс, ну вот...
По-моему, там еще будут смешные.
Ну, то есть, вот если дифференциал вот от этой нижней формы взять, это будет вот что-то типа вот этой DXI и какой-то член от R приходящий. И тогда из этого уже будет следовать, что форма дома именно вот так и будет. Ну, можно такую взять.
Нет, действительно, вот здесь, вот эта часть должна представлять классы.
А тут тех по бокам вообще.
А тех, по-моему, должен. Я еще много что-то путаю, но, по-моему, должно быть. Смешанно, иначе просто с точностью будет, с замкнутостью будет проблема. Ой, sorry.
Ну там просто вот если вот этот дифференциал...
No, if you have this form without these terms, well, in one coordinate, assume that in one chart you have this form without those two terms. But in another chart, you have this thing is added here. So when you substitute here, you get that this term appears. Yes. So as far as I remember, we indeed can delete this term, but not that one. So yes, that's almost all the ideas, but now we want to fit them together. Yes, by the way, during this discussion, we almost understand just what you told me just now. This is a general fact about Tom class and Euler class. If we have a bundle, if we have a base, yes, we have phi here, and indeed Euler class can be defined to be phi star over Tom class squared, yes? And this was our definition. Tom class, but Tom class lives in cohomology with compact vertical support and cohomology of E. Well, look, except for there is a projection, but also there is a zero section. Instead of integrating, we can just take pullback alone phi. Moreover, there is a well-defined. Another way to say with this. Okay, we can forget about this compact vertical. If we have a plus in compact vertical, we can forget about the fact that it is. Then go to usual cohomology of E. Well, and then we can take pullback along I. And in usual cohomology, we know that there is homotype invariance, so this actually is isomorphism. This one is not an isomorphism, but this map is an isomorphism. So we arrive, and here. So there is another way to arrive from nth compact vertical cohomology of E to nth cohomology of N. And this is again the Euler class. So we can either take the square of Tom class and then integrate, or we can just take the pullback of the Tom class using these maps. This is a good exercise why it is so the same, and actually the explanation is exactly that what you said. Here we must have Euler class to obtain that after square the integration we get zero. We get the Euler class. Well, still have something.
Вот если у всех этих областей у альфа границы это многообразие, там можно просто, по идее, взять вся альфа произвольная, потом на пересечениях с у альфа определяется кси-бета, а дальше можно продолжить допытывать упреживание на...
Нет, ну так можно, конечно, да. Но вот хочется, чтобы у нас
Нет, кси-альфа
не было
остается явной
сущности,
формой.
и мы хотим их написать явно через... Вот вы один раз выбрали вещи. У нас есть разделение единицы и наши функции. Тут все на самом деле через них пишется. И, то есть,
И вот эти кси-альфы тоже.
Кси-альфы тоже,
Как
да.
легко пишутся. Ну как легко. Потом объединять эти кси-альфа в одну тоже с разбиением, ведь так?
Нет, объединять их в одну просто наивно, потому что они совпадают на пересечениях. Поэтому они просто берутся, объединяются. Ничего не надо. Они просто автоматически дают. Если у нас есть формы на каждом кусочке, они совпадают на пересечениях, то у нас есть форма на всем вместе.
Да, но как эти объединяют?
В каком смысле вы хотите?
Нет, просто взять сумму ро альфа кси альфа. Это формально корректно определенное.
Ну да. Но она просто равна то же самое.
Да.
Нам как и так придется что-то продевать, потому что у нас про кси нет никакой информации вне пересечения.
Есть и существует ро альфа.
Ну да, объем.
И h СПБ, которые тем более определены тоже.
То есть идея в том, что смотрите, на всех этих этапах нам не надо заботиться о замкнутости, и это можно склеивать с помощью разбиения единиц. Well, actually, our time goes to an end. And I suggest you try to yes, to solve this problem up to end. And when you solve this, then the next problem, which is very natural, is to compute the Euler class of topological bundle over CPN, but actually recommendation is that it is easier to compute the Euler class of the dual of topological bundle of CPN. Why the dual of topological bundle is better?
Because it has sections global.
Actually, the main idea is that if you have a CPN, yes, then you always can embed it in CPN plus 1. Yes? And tautological bundle, dual of tautological bundle is the normal bundle of CPN in CPN plus 1. So its total space is automatically embedded. It's not some abstract space. It is automatically a subspace of CPN plus 1. No, it's not embedded. It's related to a program file, but it's just an easy observation that due to the tautological bundle is the normal bundle of CPN. And the question is to compute the the tone and Euler class for it. Well, so that's all for today. So once more, the next two lectures will be online, most probably, and we will discuss by email.
So should I write you an email?
Well,
Should I write you an email in advance?
yes, if you haven't wrote me yet, please write me to once more. A.Gaifullin, Sculptor. And I will reply to everybody